In the last lecture, we talked about how you can take an RF and gradient waveform pair and compute the forward SLR transform of that pair so that you can calculate its spatial or spectrally selective profiles. In this lecture, we're going to go the opposite direction. So a remarkable fact is that given the polynomials a sub n and z and b sub n of z of a given RF pulse, the SLR transform can be inverted to produce b1 of t, even that is the RF pulse that generated these polynomials, even at large tip angles. So that means that designing these two polynomials is equivalent to designing b1 of t, since they are invertible to get this waveform. This means that we can this gives us a way to specify a profile, calculate the corresponding polynomials, and then get an RF pulse that generates those perfectly. So we've seen the forward SLR transform in the last lecture, where we go from an RF pulse to the two polynomials. Today we're going to learn the inverse SLR transform, that is, going from the polynomials back to the RF pulse. The inverse SLR transform is going to be based on peeling off the rotations recursively. We're going to have the aggregate rotation of the entire pulse, and we're going to peel off rotations starting at the end of the pulse, going back to the beginning of the pulse. So one step in this peeling off operation, one step of the forward SLR transform is that the j minus first order polynomials a sub j and b sub j are equal to a unitary rotation matrix q sub j corresponding to the rotation at time point j. So this is going to have c sub j minus s sub j complex conjugate z inverse s sub j c sub j z inverse. Here I've combined the effects of the rotation and the RF at time point j into a single rotation matrix. And the polynomial after this rotation is applied is equal to the polynomial before this rotation is applied, multiplied by the rotation parameters of this time point. So then these previous ones are the j minus second order polynomials that you have immediately after the rotation from the previous time point. So if we want to go backwards, we need to calculate the inverse recursion. That is, what is q inverse? And we can use a sub j here for the jth time point. That is, what is q sub j inverse such that q sub j inverse times the polynomial after that rotation is equal to q sub j inverse times q sub j times a sub j times the j minus first order polynomials, the j minus second order polynomials, which is this, which gives us the polynomial back. That is, how do we invert this rotation matrix? What is the inverse rotation matrix that gets us back to the rotation immediately following the previous time point? Okay, so q sub j inverse is this guy inverted, right? This is the definition of q sub j, so inverse. Then we calculate its determinant and transpose everything. And what we get out of that is z times c sub j z inverse s sub j complex conjugate z inverse minus s sub j c sub j, which is equal to c sub j, if we multiply it through by z, c sub j s sub j complex conjugate minus s sub j times z, and then c sub j times z, which is equal to q Hermitian, it turns out. And we go from here to here by taking advantage of the fact that the determinant of q is c sub j squared times z inverse plus s sub j complex conjugate times z inverse is equal to z inverse, right? Since c squared plus sj squared is equal to 1. Okay, so what that means is that the polynomial from the previous time point is equal to the polynomial at the current time point times this inverse matrix, or this Hermitian matrix, this transpose matrix. Sorry, C sub j, S sub j complex conjugate, minus S sub j times z, and then C sub j times z, which is equal to C sub j, A sub j, plus S sub j complex conjugate, times B sub j, times z over z minus S sub j, A sub j, plus C sub j, B sub j. Now, we're going to know A sub j, B sub j at each stage of the back recursion, right? We're going to start with the final rotations, where j is the last time point. We're going to have those polynomials. We'll peel off the last rotation, and we'll get the j, A sub j, and then B sub j minus 1. We'll keep peeling off, and every step we'll have the current overall rotations. So we know that at each stage of the back recursion. Also, we know A sub j1, B sub j minus 1, one lower order than A sub j, B sub j by 1. That means that the leading term of A sub j minus 1 must cancel out. That is the highest order term. And we also know that the trailing, or the lowest order term, of B sub j minus 1 must cancel out. That's because the recursion gives us a z here, so that cancels out all the minus z term. So we know that that has to cancel out. So then we have that C sub j, AJJ minus 1, plus SJ conjugate BJJ minus 1 must cancel out. That is the leading coefficient of AJ minus 1. And then the zeroth order coefficient of B sub j minus 1 must cancel out as well. These are the two coefficients that we get after that multiply with the rotation matrix. Those have to cancel out too. And you can further show using the magnitude constraint that these are actually the same condition. And make it, if you solve this expression for one of the A sub j or B sub j and then substitute it in here, you can get the other condition. So overall, what this means is that we can derive the RF at t sub j from either one. That is the RF sample at time t sub j from either condition, using either condition. So if we choose the lower order condition, that is this guy, and we can solve that to get the RF sample at time point t sub j. So here it is stated here. We can put them on opposite sides, get them in terms of a ratio. And so that is, we have this bj0, aj0 term because we have the two polynomials, and that is equal to the ratio of sj over cj, which is equal to I times the e to the phase of the pulse times tangent of the flip angle of this, the phase of this sample times the tangent of the flip angle of this sample divided by 2. We can solve this guy then to get theta sub j, the flip angle, which is equal to 2 times arctan of the magnitude bj0 divided by aj0. The units of this will be radians. And then the phase is going to be angle of minus I times bj0 divided by aj0. So overall, the RF waveform is, in Gauss, 1 over gamma delta t times theta sub j e to the I phi sub j in Gauss. So now that we have the inverse SLR transform, we can specify an overall algorithm for RF pulse design with the Chenard-Leroux method. So the basic algorithm, here I'm illustrating a pi over 2 rotation, or an excitation pulse, 90-degree excitation pulse, around an x vector. The first step is to choose a flip angle profile as a function of space. So ideally we'd always be exciting a rectangular function. Here's the excitation flip angle. This gives us the rotations that we want as a function of space. So here's the ideal flip angle profile for an excitation. Then we use that to calculate the ideal beta profile, which is sine of theta of x over 2. And that gives us this, okay? This is our ideal beta profile that we want to excite. Then we approximate the ideal beta profile with a polynomial b sub n as a function of z, which is e to the I gamma gx of delta t. So that is z here is defined as e to the I gamma gx delta t, as is written here. We get this polynomial using a filter design method, which we'll talk more about later. So that is, the b sub n coefficients are a low-pass, discrete time filter. There are many, many ways to calculate this. The simplest of which is to use a windowed sinc function. But you can also use built-in MATLAB functions like FIRLS for least squares filter design, FIRPM for Parkes-McClellan filter design, or your own method. Then you apply the magnitude constraint, since we know that a sub n of z squared plus b sub n of z squared equals 1. That means we can use the amplitude of the b profile to calculate the amplitude of the a profile using this relationship. And that gives you 1 minus b sub n of z magnitude squared. So this gives us our a profile, a or alpha profile in magnitude. For the 90-degree pulse, it would give us basically a flat 1s in the stop band, and in the pass band, you'd get square root of 2 over 2 on average. Then you can solve for the phase of a sub n of z and combine with its magnitude to get the complex valued polynomial a sub n of z. So that is, here I'm plotting the real and imaginary parts of this. Typically you'd get that most of it's in the real part, most of the energy of the profile is in the real part, and you'll have some phase blips here in the imaginary part. So a sub n of z is not unique, and there are many possible phase profiles. That's a topic for another day. But the most useful solution is the minimum phase a sub n of z, which gives the minimum integrated, not peak, RF power. So this ends up being what you want to use for pulse design, since we usually want to minimize the total power of an RF pulse. Now, after this step, we have both complex valued a sub n of z profile and the complex valued b sub n of z profile, and they're compatible with each other. So we can use the inverse SLR transform to obtain the RF pulse from these two fully specified polynomials. So let's go a little deeper on how we get the minimum phase version of the a sub n filter and why we want that. So first, we would write a sub n of z as a sub n magnitude of z times e to the I angle, the phase angle of a sub n of z. So we know what the magnitude has to be, but because we go in knowing what the magnitude of the b filter is. So this is known from magnitude of b sub n of z. But what we're dealing with here is the fact that once we have that, we still don't know what the phase needs to be. Okay, so let's start. We'll take the complex logarithm of a sub n of z, which gives us log magnitude a sub n of z plus I times angle a sub n of z. Now, if a sub n of z is a minimum phase filter, it has no poles or zeros on or outside the unit circle. They're all inside. And log a sub n of z is what's called an analytic signal. That is, it is 0 for negative time. And furthermore, its phase angle for this kind of signal is equal to the Hilbert transform of its log magnitude, which again, we know its magnitude, so we can calculate its log magnitude and subsequently the Hilbert transform of that. And that is equal to dft of j times sine of n times dft inverse, as discrete Fourier transform inverse, of log of the magnitude profile, which I'm running out of space, so I'm just going to use a dot for that. Okay, so to calculate it, you take the log of the magnitude profile, you take its inverse discrete Fourier transform, you element-wise multiply it by 1 or minus 1, depending on the index, the sign of the index into the DFT. Then you multiply it by square root of minus 1, you take the forward discrete Fourier transform, and you get the phase angle. And we can calculate this directly, since we start out knowing what the magnitude of the filter's response is from the magnitude constraint. And then overall, the complex valued polynomial a sub n of z is equal to magnitude times e to the I Hilbert transform of log a sub n of z, log magnitude a sub n of z. Okay, so why do we want the minimum phase a sub n of z that we build this way? The minimum phase a sub n of z's impulse response, or coefficients, will have the largest DC coefficient of any filter with the same magnitude a sub n of z. This leads to minimum power in the pulse. So minimum RF power. And we can illustrate this. So consider a forward recursion where we have the polynomial at time point j minus 1. We multiply by the rotation parameters at time point j to get the polynomials at time point j. The DC or zeroth order coefficient of the a sub n polynomial, you can see pretty quickly here, is the product of all the cosines of all the pulse, c sub n minus 1, dot dot dot, c2, c1. Right? Since you're going to start out with a c here, and then you just keep hitting c's as you multiply through time with the pulse. For small flip angles, c sub j is which is defined as cos theta j over 2 is equal to 1 minus 1/2 theta j over 2 squared by Taylor series, which is equal to 1 minus 1/8 theta sub j squared. Then that means that the zeroth order coefficient of A is 1 minus 1/8 theta sub n squared times 1 minus 1/8 theta sub n minus 1 squared, dot dot dot, all the way down to 1 minus 1/8 theta sub 2 squared, 1 minus 1/8 theta sub 1 squared. Okay, and so this again is the DC coefficient of the A0 filter, and the minimum phase filter has the biggest of these coefficients. Okay, and so that if we multiply all these together, we basically neglect all cross terms where the theta sub j's, the thetas multiply into each other. Then this DC coefficient is approximately equal to 1 minus 1/8 times sum over n equals 0 to n minus 1 of theta sub n squared. Now recall that theta sub j is equal to gamma times magnitude b sub 1 j times delta t. So that means that the DC coefficient a sub n 0 is equal to 1/8 times gamma delta t squared sum over j equals 0 to n minus 1 magnitude b sub 1 j squared. And so the filter with the largest DC coefficient here corresponds to the pulse with the lowest power. Since the smaller the overall power, which is the integral of the pulse squared, the larger the DC coefficient. Okay, so overall then the minimum phase a sub n of z solution gives the minimum RF power. This is almost always what you want. I have yet to come across a situation where it's not what you want. To summarize, SLR pulse design proceeds by first designing the beta filter b sub n of z according to the desired flip angle profile, and then a sub n of z is designed to be magnitude consistent with beta, the beta profile, and also yield the minimum power RF pulse. Then the inverse SLR transform can be applied using these two polynomials together to get the samples of the RF waveform that produce these polynomials. So we'll go through some design examples. So some types of beta polynomial designs are linear phase. This is the most common. It's a type of pulse that looks like a windowed sinc function, basically. It's perfectly refocused with gradient reversal. That is, you play a gradient trapezoid during the pulse and then you play half its area afterwards. It's the most common. It's symmetric in time. You can flip it backwards or forwards and you'll get the same waveform. It's not the most selective generally, and it has the maximum peak power, but not by a huge amount. The minimum phase pulse is an alternative that can be used for saturation or inversion. In this pulse, the flip occurs as late as possible for a given target beta profile or amplitude profile. That is, most of the energy is concentrated at the end of the pulse, so that's when most of the flip happens. It's the most selective pulse the beta filter that we can design. That is, it gives you the sharpest transition regions, the narrowest transition regions in the profile for a given pulse duration. It does not perfectly refocus because it leaves a small nonlinear phase that can't be refocused with gradients. It has almost the same peak power as the linear case. The maximum phase design is the same as the minimum phase, but it's just reversed. This is a rare one. I haven't had any reason ever to use this design. Well, I should put a caveat on that. I have used it once for temperature mapping, where I wanted the TE period to start at the beginning of a long pulse so that you got temperature phase contrast developing out throughout the rest of the pulse. And finally, we have quadratic or nonlinear phase pulses. This is a much more expanded topic here for minimizing the peak amplitude of the peak power or peak amplitude of RF pulses. So here, in this case, you have a complex valued waveform with real and imaginary components. It gives you identical total power as a min or max phase pulse with the same magnitude profile, but it can have, by specially designing it to go into both real and imaginary channels of the RF, you can end up with much lower peak RF power, which is important for meeting certain hardware constraints. So again, these pulses have the same power, so they have the same SAR as the original pulses, as the original linear phase or minimum phase pulses. But they have a much lower peak amplitude, which can be important if you're doing excitations or saturations with super high time bandwidth products. We've also designed pulses this way for multiband excitations because you get such a large increase in peak RF power for multiband excitations. So here's an example of an SLR excitation pulse design. You again start with the profile that you want in space. That gives you the beta profile, in which for an excitation pulse has amplitude √2/2. You use a filter design algorithm to take the characteristics of this profile and give you the samples of the FIR filter that generate it. You can see that this already looks like has an RF pulse-like shape. Then you use this profile to calculate the compatible alpha profile. Here's its amplitude. Sorry, here's its real part and its imaginary part. That gives you an alpha polynomial, which is mostly zeros except for the very end where you have a giant DC spike there, and that means that this is a minimum phase pulse that gives you the highest DC coefficient or the lowest RF power. You take these two sets of coefficients and you can imply the inverse SLR transform to get the RF pulse, and that's this guy. The final RF excitation profile is this, right? So this curve is the MX component, and this curve is the MY component. Here's an example of a spin echo or refocusing pulse design. So in this case, we have a pi flip angle that we want, and so that gives us a beta amplitude of 1. Again, we get an RF-looking kind of shape in the beta polynomial. We calculate the compatible alpha polynomial, which now has much larger sort of phase variations through it. And that gives us a pulse still that has a very large DC coefficient. Sorry, this is the alpha filter that has still a very large DC coefficient, but also has more features away from that. Then the RF pulse is obtained by taking these two polynomials and putting them into the inverse SLR transform. Gives us the RF pulse, which then has this spin echo profile, which is equal to beta squared. So to just kind of zoom in on this problem, here's the desired beta profile we want, right? So this is the linear response, the response of the linear discrete time filter, beta filter, that we generate. This is the filter that we get from this desired beta response. And if you compare that to the RF pulse, you can see how the RF pulse has a narrower main lobe than this filter, right? And that kind of makes sense because we know that there's a bandwidth narrowing effect as we scale up a linear filter to excite large flip angles. So you have to narrow the pulse shape, the main lobe. So any design algorithm to generate a target, a given rotation, or a given slice profile, should have a narrower main lobe than the main lobe of the linear design, in order to widen that pass band. And then this RF pulse generates the spin echo profile that we want.